Hello, welcome to my talk. This talk is on a special and interesting topic. What are fruits? This seems a very simple question, but the answer might not be that obvious. For example, the granular materials such as sand, salt, flour, they could flow like water. Are they flows? In this talk, I will answer the question from a very different point of view, and will tell how we can determine what are flows and what are not from the real physical understandings. A simple and the most understandable definition for a fluid would be: a fluid is a substance that flows, including liquids such as water, gases such as the air, plasmas, and more. This definition gives the most special feature for fluids when compared to solids. However, this definition might have difficulties for some special materials. For instance, the fine granular materials could flow like real fluids, such as the dry fine sand, the fine salt, or the flour. See this picture. This is a salt flow, but they are not fluids. And you will see the answer later in this talk. While some other materials look like a solid, but they are actually fluids. For instance, the famous pitch tar from this famous pitch job experiment. And here tar looks very similar to solid. Let's see an experiment of the flows of different materials. Here we have three different materials: the flour, the salt, and the water. The first example is the flow of the flour. We can see the flour flows through the funnel, but not very smooth. We have to shake the funnel to make the flour flowing. The second experiment is the flow of the salt, and we can see the salt flow through the funnel is very smooth and fast. The third experiment is water. Obviously, water could flow through the funnel easily as we expect. The result of the water flow in the container is a flat surface. If we follow the simple definition of fluids, all these three materials can be fluids. Is this true? A more accurate definition would be as this technical definition: fluid cannot sustain a tangential or shear force when at rest, and could undergo a continuous change in shape under such a stress. In other words, under shear stress, the fluid flows. Based on this definition, we can compare the fluid and the solid. Fluid would flow under the application of shear stress, but the solid cannot. Fluid cannot sustain a shear stress without flowing, while the solid can. Fluids have some unique properties that solids do not have, such as pressure and viscosity. In this slide, we are going to look at the properties of fluids. Here, we look at the common properties for fluids and solids. Density is a property related to the mass of material in a unit volume. The air has a density as 1.225 kilograms per cubic meter. Temperature is a property that determines the degrees of hotness or coldness, or the level of heat intensity. Speed of the sound. Both fluids and solids are the elastic material in which the sound travels a certain distance per unit time. In air, the speed of sound is about 340 meters per second. In water, it is 1,500 meters per second. In steel, it is about 6,000 meters per second. Here we also show the unique properties of fluids. Pressure. The surface of an immersed body in a fluid is bombarded by a large number of molecules of fluid moving at random, so to create force on the surface. So in water, the pressure is calculated as P0 plus no GH. Viscosity. The fluid viscosity is a result of the molecular interactions in fluids, which has a tendency to resist sliding between the layers in fluids. This is different from the solids. There might be a deforming, not sliding. For the air, its viscosity is 1.8 times 10 power of minus 5. And the water, the viscosity, it's 10 power of minus 3. In the next few slides, the fluid property, pressure, will be examined for the most conventional fluids, water and air. The first example is the static pressure in water. From the Navier-Stokes equation, we can deduce the equation for the static pressure in water is given as this. Here, rho W and G are the water density and the gravitational acceleration respectively. In water, even in the deepest ocean, like the Mariana Trench, which is about 11 kilometers below the sea level, the water density and the gravitational acceleration would change less than 5% and 0.3% respectively, and thus both can be regarded as constant for engineering application. Therefore, we can easily obtain the pressure expression as this. Here, P0 is the atmospheric pressure at sea level, given as 101,325 pascals. It's roughly as 1 bar of 100,000 pascals. it's close to the pressure of 10-meter water height. We can take H equals 2 minus Z as the water depth. So we have the expression for the pressure in water. We can see the absolute pressure in water linearly increase with the water depth. Or more conventionally, we can write the gauge pressure delta P like this. So the gauge pressure in water is proportional to the water depth. In the deepest ocean, the Mariana Trench, with the depth of 10,995 meters, the static pressure at the deepest ocean would be about 1,100 bars. The force on 1 centimeter square, or the size of the thumbnail, is 1 ton force, or 10,000 newtons. The equation for the static pressure in the atmosphere had the same form as that for the pressure in water. Here, the density rho A. Generally, the gravitational acceleration g would be a constant, since up to the most outer bound of the Earth's atmosphere, the common line 100 kilometers above the sea level, the change of the gravitational acceleration would be within 3% reduction. The air density, rho A, is the function of both pressure through the gas equation and the altitude Z through the temperature T in this plot. So from this ideal gas equation, we can obtain the air density given in this formula for the troposphere. We can obtain the pressure expression in the troposphere, which is up to 11 kilometers above the sea level. So we can see the pressure decreases with the altitude. For the full formulation for the pressure in the atmosphere can be found in the reference. So if we draw out the pressure change with the altitude, we have the curve at this. And if we look at the two interesting altitudes, the first one would be the altitude for most commercial flight at about 11 kilometers above the sea level, where the pressure would be about 22% of the pressure at the sea level, P0. And on the Everest, at the height 8,848 meters, their pressure would be about 31% of the pressure at the sea level. Now we will examine the second unique property of fluids, viscosity. Based on the Newton's law of viscosity, the viscous stress can be defined as the viscosity mu times the gradient of the velocity with regard to y in this figure. Here mu should be called as the dynamic viscosity, and it can be obtained from the Newton's law of the viscosity as this. However, in the fluid dynamics, a more useful viscosity is called kinematic viscosity, nu, defined as the dynamic viscosity mu divided by the fluid density as this. Here we list some common fluids. If we compare water and air, we can see the dynamic viscosity of water is much higher than the air. It's about 50 times larger. However, the kinematic viscosity of the air would be 15 times of the water, can be seen here. And also from this table, we can see some very sticky fluids, honey, mayonnaise, and sour cream. Honey has a viscosity 3,000 times as that of water. In this slide, the relation of the viscosity and the temperature would be given. So from the plot we can see when the temperature increases, the viscosity decreases. See the change of the viscosity here. And for a comparison, the molten iron is plotted in here. But it should be noted the temperature range is for 1550 to 1800 degrees. For the gases, the air, helium, hydrogen, we can see when the temperature increases, the viscosity increases. Now we look at some very interesting experiments. There has been an argument over the black pitch. From the appearance, the black pitch is solid, but the experiments have proven that the black pitch is a fluid. From the pitch drop experiment, a fluid with an enormous viscosity. The most famous pitch drop experiment is the one at the University of Queensland, Australia, started from 1927. The record shows there is roughly a drop in 9 years. And an interesting fact is Professor Manstone has taken the custodianship for 52 years of the experiment, but he never saw an actual drop. Another famous pitch drop experiment is in Trinity College Dublin in Ireland, and the drop was captured on camera on 11th July 2013. Now researchers have calculated the viscosity of the black pitch based on the drop times, and it is calculated the average viscosity is 8 million, which is 8 billion times larger when compared to the viscosity of the water. From Wikipedia, we can find some more pitch experiments. The earliest experiment on black pitch is the one at the University of Glasgow, Scotland, in 1880s. Lord Kelvin placed bullets on the top of the pitch and the corks at the bottom, and over time the bullets sank and the corks floated. This is a different way to prove the black pitch is a fluid. I would like to say a few words here. The author finished his PhD study at the University of Glasgow under the supervision of Professor Roderick Gobles. A pitch job experiment is discovered at the Aberystwyth University in Wales. This experiment started in 1914, which was 13 years earlier than that in the University of Queensland. But there is no job produced yet, probably due to the low average temperature. Now we look at how we can distinguish the solids and the fluids. We might have different ways to distinguish fluids and the solids. In the next two slides, we will see what will happen if a shear stress is applied to fluids and to solids. Suppose we have a small fluid element, as seen in this plot. If a shear stress tau to 3 is applied on the top of the element, based on the definition of fluid, there will be a flow at this, and due to the flow, a fluid viscous stress or the friction is induced within the fluid due to the velocity gradient given as this. And this viscous stress could balance the applied shear stress given as this. Hence, under this condition, the flow would be steady. So this is very different from a small solid element when the shear stress is applied. See the next slide. So here, the small element is a solid. We apply the same shear stress tau to 3 on the top of the element. We can imagine under the applied shear stress, a deformation would be caused for the element. It should be noted the deformation is very small, hence it is not a sliding or a flow. Due to the elasticity of the solid, there will be a shear stress tau 32 produced to balance the applied shear stress on the vertical surface at the right-hand side, so to avoid an infinite rotation of the element. This is required by the Cauchy symmetrical stress tensor, given as tau 32 equals to tau to 3. In the next two slides, we will prove why the granular materials are not fluids, and we will examine the problem in 4 different ways. Is there pressure in the granular materials as that we have in the fluids? The answer for this is no, because the static pressure, as we see in the figure, if there is one in the granular materials, it is not caused by the molecules acting on the surface. Thus, there is no conventional pressure in the granular materials. Is there viscosity in the granular materials? We can assume a slide in the granular materials, and if we move this slide, we will expect the friction between the granular materials and the slides. However, the friction would be very different from the conventional viscosity, which is caused by the molecules acting on the slides. Therefore, the answer for this is there will no viscous stress in the granular materials. Here, if we apply a shear stress on an element in the granular materials, superficially we will expect the flow of the granular materials. However, if we reduce the element to smaller than the granular, then the granular material would perform exactly same as solid, as this here. Therefore, the granular materials cannot be flowed. The last factor would be the free surface at rest, as we see in these three cups from the experiment I showed earlier in this talk. So for different material, water, salt, and flour, from the experiment, the materials flow to the container from top. We can see the free surfaces are very different. For the water, because it is fluid, thus its free surface is flat, with no shear stress on the top of the fluid. We can see from this analysis there will be no shear stress on the particles at the flat horizontal surface. For the salt, a flat cone is formed, while for the flour, a sharp cone is produced. The reason for this might be their significant difference in their density, 2.16 kilograms per liter for salt against 0.593 kilograms per liter for the flour. So if we examine the covered surface, we can see there will be shear stress tau acting on the element on the top of the granular material. And the sharper the cone, the larger the shear stress. Here we can see for the granular materials, the shear stress on the top of the material would not cause a flow motion, as we see in the fluids. Therefore, we can say the granular materials are not fluids.